Okay.
Today's webinar will be moderated by Mr. Professor Umut Rıfat TUZKAYA, Vice-Chancellor of Yıldız Technical University.
Okay. Mr. Arthur, let me start the
yes, of course.
webinar. Okay.
I pass the floor Mr. Atila KESKİN, Vice President of the IRRB.
Good morning, good afternoon, good evening, esteemed participants. Welcome to Assets for the Automatic and Autonomous Operations webinar. Before we start, I would like to give a thanks to all of the speakers who shared valuable knowledge with us. And also, I would like to express my gratitude to UIC and IRRB, just a second. IRRB for their efforts to enable to this seminar to be held at the international level. Now, I would like to invite the Director of Rail System Department of UIC, Mr. CHAVANEL, to make the welcome speech.
Dear participant, Rail System Director Mr. CHAVANEL was unable to join us today due to other obligation, but the message from Mr. CHAVANEL is recorded and to the participant, and at this session will be now played.
Dear Chair, dear Vice Chairs, dear colleagues, good morning, good afternoon, and good evening. The IRRB was very active, notably through very appreciated online workshops or webinars. I will simply recall them. Workshop on new railway technology and innovation in November 2020, Railways in the Transport Market Competition and Cooperation in November 2021, Sustainability and New Digital Trends for Heavy Haul in December 2029, Digital Tools for Railway Operations, Maintenance and Safety in July 2022, and Autonomous Technologies in Rail, Anticipation and Expectations in June 2021 with around 400 participants. In the continuity of this webinar on ATO, is organized today this one entitled Asset for Automatic and Autonomous Operation. These two webinars on ATO are very important for UIC. Indeed, they are perfectly aligned with UIC activities and vision. If I may, I will detail. UIC published its vision of rail in 2030 on the 1st of December last year. Indeed, there is for the first time today a unique momentum for a radical model shift from road and aviation to railways worldwide. Adaptation to climate change is becoming a major concern, shared worldwide, and the urgency of which has been recalled by the Intergovernmental Panel on Climate Change. The Railway System Forum has integrated in a systemic approach major technical breakthroughs through its multi-annual work programs based on capacity, quality of service, and continuous improvement of railway services and innovations. Concerning capacity, Rail System Forum will insist on traffic control centers and crisis management, automation facilitating the increase in the number of trains and supporting the cost leadership strategy with DAC, ATO, artificial intelligence, robotics, automatic inspections, and 5G use cases. Concerning quality of service and continuous improvement of railway services, the Railway System Forum will insist on operations and safety. For operations, Railway System Forum will focus on harmonized operational rules, enabling robust and resilient timetables, increasing punctuality, and improving management of disrupted situations. It will also insist on tools for increasing the length and healthiness of freight trains. Predictive maintenance for better reliability and availability of infrastructure and running stock, and better integration in operations. reduction of railway noise, facilitating the acceptance of the increasing number of trains by neighbors of the railway lines. For safety, it will focus on new methods for safety demonstration and risk analysis processes, aiming at certifications and approvals of innovative systems at global scale. Concerning innovations, the Railway System Forum sent the first FMCS specifications in October 2022 to the European Union Agency for Railways. The midterm objective of Railway System Forum is notably the full definition of FMCS for market readiness. The Railway System Forum will support the development of lighter trains, and it will continue to work on reduction of energy consumption and emissions, on resilience of railway infrastructures and running stock to climate change, and on railway digital modeling. Thus, you can see how automation and digitalization, and therefore especially ATO, are key enablers for capacity, quality of service, and continuous improvement of railway services and innovations. That is the reason why I thank you on behalf of the UIC Director General, Mr. DATEM, for organizing this webinar today. Please know that you can count on the full support of the whole UIC for your future webinars. I wish you an excellent webinar.
Now I would like to say a few words, dear participant. It's very nice to host you in this platform. To each of you, welcome again. First of all, the limited resources in our world is one of the undeniable facts that we are faced with the effective usage of those limited resources. It's very necessary for our future generations. The use of automated and autonomous technologies will be enabled to use the limited resources effectively. Within the following years, we will see more automated and autonomous technologies applied to railway and the other transportation modes. Those technologies are expected to effectively replace the increasing demands for passenger and freight transport, safety issues, human errors, and increasing traffic jams on the railways. In addition, it enables the central control using the advanced communication and the internet technologies such as high-speed internet, 5G technology, Internet of the Things, spatial short-distance communications, digital detection cameras, and the artificial intelligence-based methods. It should be collaboratively by railway companies, research and the relevant stakeholders, including countries, to facilitate the development and the deployment of the automated and autonomous technologies for the future users without reducing their levels of security. Now, I am very happy to invite Professor Dr. Umut Rıfat TUZKAYA, the Vice-Chancellor of the Yıldız Technical University, to chair our webinar. Yes, Umut Rıfat TUZKAYA.
Thank you very much, Mr. Atila. I think you can hear me. Dear chairs, vice chairs, my colleagues and participants, welcome to this precious webinar named Assets for Automatic and Autonomous Operations, which is organized by the Research Board of the UIC. As Mr. Atila told, today I will be moderating this significant event, and this is a really great honor for me. And I want to say thank you to the UIC for accepting me. If you want, I would like to introduce myself briefly to you. I'm a faculty member at Yıldız Technical University, Department of Industrial Engineering. And I have been working as the vice rector of the university for 2.5 years. In the last 5 years, actually, I worked as the coordinator of some projects like Istanbul Logistic Master Plan, prepared for the Istanbul Metropolitan Municipality. Preparation of a strategy document for Taşımacılık AŞ, which is a company of Turkish State Railway. And also Sustainable and Smart Mobility Strategy and Action Plan project for Ministry of Transportation. It is nearly finishing. And also worked as a consultant in the Turkey Transportation and Logistic Master Plan projects. So I am a little bit related with these issues, but railway industry, actually a very specific industry and very important for most of the countries, also for my country, Turkey. And UIC is making very good things, and UIC is a very important foundation. So I want to highlight some important points about the UIC, which I found from the resources of UIC again. Actually, UIC is a tool that enables joint working, thinking, action, and process. And UIC is first and foremost a repository of railway expertise and a forum for sharing experience and seeking solutions whose aim is to bring about greater consistency between railways worldwide. It also facilitates the development of international rail links, which benefit all rail users. And UIC's second major remit is to help the railways prepare for the future. For each region of the world, UIC has drawn up a strategic vision, offering a consistent framework for railway development. And one part of preparing for the future is investing in innovation, new technologies, and digitalization. And that's why today's topic, I mean assets for automatic and autonomous operations, is very important for the stakeholders of railway industry in terms of the innovation and technology. And we will listen 5 important presentations today. And now I want to finish my introduction and give the floor to the first presenter. But before that, I want to emphasize some rules. For example, please turn off your microphones and cameras during the presentations, and also everybody is like that now, I see. And you can use the chat box for questions. To ask a question during the question and answer session, please select the raise your hand button. I will give the word to you. And if you have any technical problem, again, you can use the chat box and someone from the UIC team will help you. For each presentation, we have 20 minutes. Maybe little tolerances can be given. If we have time at the end of each presentation, I can give the words for some questions, but actually we are planning to make a discussion after all presentations has finished. Okay, I think the first presenter, Mr. Andreas Lipka, the head Migration Digital Automatic Coupling, DB Cargo. And the title of the presentation is The Digital Automatic Coupler, a Game Changer for the Rail Freight Sector. So we are waiting your presentation. Thank you.
Yeah, thank you very much. Hello all together. I hope you can see already my screen here.
Yes, we can see.
Okay, so at first I have to say a very warm welcome to all of you to the presentation about some insights into the development for the digital automatic coupler, which is currently being done by more than 80 companies in more than 30 countries all over Europe, with the aim to innovate and to digitize and automate the rail freight network on the 1435mm infrastructure in Europe. As already mentioned, I'm head of the migration planning team for the digital automatic coupler, in a dual responsibility. First in my home company, the rail freight subsidiary of Deutsche Bahn, DB Cargo, but in the same position in the European duct delivery program, the EDDP, there's a work package named Migration 2. So, and this is, I think, a very good precondition to have a complete overview about the whole duct migration process and to keep it running. As we know, the current standard coupler, the UIC coupler with the burn safety area and so on, is more than 100 years old. We need completely manual work here to connect or to disconnect hooks, spindle, brake hoses, and so on. And we want to get away from that, but not only to reduce coupling efforts. Of course, this is also a task. But the major aim is by replacing the mechanical coupler and to add it automatic and digitized part here is to digitize rail freight and to automate rail freight. It's not about coupling as the first target. It's rather something where we say it's a must, yeah? And therefore we need an automatic and digitized coupler. But the major aim you see on the next page here is we see the targets we are looking for, and what we would like to achieve with the digitization and automation of rail freight all over Europe, not depending if it's an EU member country, because all this traffic is at least partially international. All over Europe, the domestic traffic is rather in the minority. So we have to think overarching from Norway down to Turkey, and from the 1435 millimeter tracks which are built currently in Spain to the same we see in the Baltic countries, Lithuania, Latvia and Estonia. So what we are looking for is, for example, sensor for state monitoring. This is currently in many countries already state of the art, but we need to gather all the information for the whole train. We need modern braking systems like the electropneumatic brake, especially on the rail freight corridors, which lack of capacity. We need there some tasks to increase capacity without building more and more tracks, because there is something more to be done, and this is by braking faster, running faster, and accelerate earlier again. And this could be done by the electropneumatic brake. We need wagon information on the whole train set. We want to, this is especially a case for automation, we would like to centrally steer via the locomotive valves and actuators, and we need interfaces to an IT backbone system, which is then offered by the RU or by the infrastructure managers to its respective customers.
Dear Lipka, I'm
Yes.
sorry, I made a mistake about the timing. I think everybody know maybe, but you have 40 minutes. In my timetable, it seems that you have a longer time. I think
Yes.
your speech is a little bit longer, so I made a mistake while talking. Sorry.
I'm
Time.
fine.
Go for it.
Thank you for that. Yeah. Okay, coming back to the presentation, this can't all be done by only a few single players or even one single railway undertaking. This is simply not possible. And in the end, we see the need for an overarching sector approach, where we have to bundle, on the one hand, the forces of the market participants like railway undertakings, but as well as authorities or national organizations, national security authorities, ministries. The UIC, of course, is involved too. And some other organizations, and on European level, we have also support by the European Commission. And this led to two different research projects, and the one I already mentioned is the European Duck Delivery Program. This is running under the umbrella of Europe's Rail, which is a joint undertaking on European level in the European Union. And this is a huge organization driven by many different companies, stakeholders like workshop service providers, manufacturers, RUs, IMs, NSAs, and many other organizations on a European level, and not only on European Union level. We have also strong participants from Switzerland, from the West Balkan countries. We have participants, and so we are not only looking within the scope of the European Union here. Nevertheless, it's driven mainly by funding of European Union here. And second is what we call the DAC for EU, DAC for Digital Automatic Coupler for the European Union project. This was launched by the German Ministry of Transport, and this was rather more or less the nucleus of the whole movement. This is mainly carried by a consortium funded by the German Ministry of Transport, where we do a lot of research work, where we do a lot of conceptual frame setting. And this program has been extended recently, a few weeks ago. And the good news is that we can continue with the testing procedures until mid of 2024 at least, and this is backed by additional budget here. So this is rather on testing, this is rather on European deployment, but this is what we need, because everywhere else where automatic coupling systems had been introduced, we had some kind of central steering organization. If it had been in Japan 100 years ago, or in the Soviet Union 70 to 80 years ago, or other parts of the world, we always had there some, let's say, overarching steering body to assure that rail freight will be updated and retrofitted with the new equipment very quickly without canceling too many customer services, and to stop the whole system. So this is very important. We need this support here. Without that, it wouldn't work. I mentioned some tests. I would like to share with you only a few impressions about this. What have we done here? For example, we brought some of the test wagons to the climate chamber in geometrically precisely defined curves. We did some measurements about the behavior of the new coupler head, and we took many different tests on the parameters of the new coupler head, because what we need is a stronger and more robust system that we have today. We want to carry longer and heavier trains. And what's currently used in passenger transport all over Europe as an automatic coupler there is not suitable for rail freight, because it's for not that often coupling movements. It's not for heavier trains, not for longer trains. So we can't use what the industry is offering us from the rack for passenger trains. So, and therefore we decided to do many tests, and this is, as I mentioned, funded by public means. In the end, we turn out with currently 2 different candidates for a coupler head. You see here on this slide the 4 coupler heads, which was where we started with in the testing program. On the top left here, you see an SA3 adaptation as we see it in on the 15-20 millimeter area, as well as we have here a Schwab design, which is a certain coupler head we see very often. For example, we see it in passenger trains in some countries. And on the right-hand side here, you see two different designs of a Scharfenberg ledge-type coupler head. And this is also a very old invention. This Scharfenberg design itself is not new. But the new thing is that it's stronger than the earlier versions, and it has a digital and automated part to assure these digital and automatic functions during the train run and the coupling procedure. So we have different manufacturers cooperating with the project and undertaking with us the research and development tasks here. And you can imagine that there's a lot of discussions ongoing on we want to sell what we have already invented, and we say it's not enough, and we have to challenge them a bit and say rail freight in future needs more than we see here. So the two candidates on the left-hand side didn't pass some of the quality gates. The candidates here on the right-hand side did it, and we have already a third Scharfenberg design which is competing with the two others. And what we see is that we need not one out of them. The best would be to take all the good ideas of all the three candidates. The third one is not shown here because it's very, very new. We need an amalgamate of the best of these two worlds, or now three worlds of coupler designs, to have the best what the market is offering. So the way won't be a decision for the one or the other or somebody else. It must be a joint effort here to bring these good ideas. The one is more smart for future operations, the other is more robust in if it comes to weight and length of train and so on. So each of them has its own strengths, and we need all of them. Yeah? So we have to bring them together. It's not a technological project. It's also a political thing to join the forces of the whole sector here. Okay, as I'm responsible for the migration planning, I would like to introduce to you the two major imperatives which are guiding us here. And the first one you can see here on the left-hand side. You see the new coupler head, not depending if it's a Scharfenberg design or an SA3 or a Schwab or whatever. It's not compatible to the current USC screw coupler system. And this means wagons or vehicles with two different coupler types shouldn't meet each other because they are not compatible. And missing compatibility is also a risk for rail freight operations and also a danger for accidents. So we have to avoid this. And all the migration planning is led by the thought they should meet each other. So we have to migrate, and this will take several years. We calculate about maybe up to 6 years, depending on keeping the services up, but having access to rail freight workshops and capacities, additional empty capacities for rail freight in rail freight workshops. We say it will take several years, and in this period we have to migrate already some vehicles, and some are not migrated until then. Yeah? So this is one of the guiding principles of our migration planning work. And second, I already mentioned, is the absence time from the customer. You see it on the bottom left here. we should be aware that our business is serving rail freight customers, so we shouldn't take the vehicles for a too long period away from the customer to do nice improvement works for our own sake. This is second guiding imperative, the principle that is leading us, reduce the absence time from the customer to a smallest possible time. And this leads us to several fields of action. What does it mean for the rail freight sector if we would like to run with two different coupler systems which are matching here and there, for example, in the single wagon system in more than 100 marshalling yards all over Europe, or in container terminals where you have maybe trains already running with a digital automatic coupler with a duck, and other trains coming in still operated with the screw coupler system. What does it mean? So therefore we have to develop migration strategies, and these migration strategies shall assure that we can offer still rail freight services over several years. The estimated time span is until 2030. That we can offer rail freight services still ongoing in single sidings, huge marshalling yards, on the highly frequented rail freight corridors, and in remote areas altogether. And I will show you a quick insight into the general thoughts about migration strategies. But it's not enough. We have to think about fast conversion concepts in workshops, and we have to increase staff resources in the rail freight, wagon workshops and the locomotive workshops for rail freight, because today the utilization of the workshops is more or less okay with the current work. Regular maintenance, work after accidents, this is covered, of course. But for such a huge effort of converting 500,000, roughly 500,000 vehicles on the 35mm network all over Europe, we need additional people. And in some countries in Europe, the labor market is already in a condition that it's really a challenge to find new people. In some places, even to replace the existing colleagues which are retiring. And then we come and say, hey, we have a huge demand for additional people in workshops, and this is really a challenge. So this is one of our, let's say, secondary tasks here. And to accelerate, for example, the retrofitting processes, we have to influence the technical layout. So we are in discussions with the manufacturers of the coupler head about the coupler design to make retrofit fast and safe, and maybe even with less trained staff, which we hire for a certain period. So this must be smarter than what was offered today. So the current coupler design is based on, okay, there's something broken, I replace it, I have the time, I have the people, I have the equipment. This has to be changed into, we have to retrofit 500,000 vehicles with 1 million coupler heads all over Europe, and we don't even have experienced old colleagues here to do all that work. So this has to be taken into consideration here by the manufacturer. So we speak from the migration planning with the colleagues which are working on the technological side of the project about the technical layout. We name it design to retrofit or design for migration. And we have some other design principles like design for operations, and after the migration it has to run properly and smoothly. And but our demands are also influencing the coupler design. Next thing is we are discussing on the framework conditions in the European rail freight sector, especially for the procurement processes for the coupler head once it's finally developed. And as well as we are doing that, we are talking about public funding programs and how to shape them, not about the money and the amount of what maybe we get as a support of taxpayers. So this is of course also a topic, but not from the migration perspective. We have a financing and funding work package also in the European Duck Delivery Program. So the colleagues are discussing that, but we have to keep an eye on the setup of the funding program, because, for example, if it's needed that a wagon has to go to a workshop in the country where, for example, the national ministry is supporting with some funding, then we would create bottlenecks. We have some learnings from, for example, the noise-reduced brake blocks in Europe. This was done in some countries very easily, and in some, depending on the national funding program, this was rather a challenge by bureaucratic work and some time limits and some other hurdles. And this shouldn't happen in the migration period until 2030 if we want to even grow in the rail freight market in the same time. So this is what we are discussing here. Of course, the whole thing has to be coordinated on a European level, ensuring synchronized and controlled migration to prevent us from seeing marshalling yards collapsing because different wagons with different coupler systems are meeting each other, and sooner or later the whole thing is a complete mess. So this is our work here, and we always enjoy to see coming new incoming members for the European Duck Delivery Program. And if the one or other from your institution or company is interested to join the European Duck Delivery Program, it's open to everybody, and it's free of charge. So the only thing is what we need is really contributing your work and your expertise, and not only people sitting there as an audience and taking the information out. This is rather not intended. So on a European level, we are running this year together with the colleagues, which is quite a management challenge, but I'm still optimistic that in 2030 we have done all this here. I mentioned migration strategies. Just one slide about that to give you a better understanding. From the almost 500,000 vehicles, we see 460,000 wagons, then a bit more than 20,000 locomotives, and the rest are special vehicles for construction sites, cranes, and things like that. And for those wagons which are running in more or less what we call separable transports, which are produced in block trains as a bicycle chain, rotating between maybe a port terminal and a hinterland terminal. These trains you can take out of business and bring them into a workshop maybe at a longer weekend. And this is quite a challenge, because 250,000 of wagons with additional workload bringing to workshops is from today's perspective not possible. So we have to increase here the capacities, but mainly not building new workshops. At least we have to utilize the existing workshops better. That means 24/7 work instead of maybe one shift or two shift patterns and schedules in the workshop we have. So we could even work here on the weekend if it's not done yet. But this means we don't have to buy additional equipment. We have to hire additional people. So, and there the labor market topic is here again. So separable transports will be brought to the workshop, and this will increase, for example, weekend by weekend, the share of vehicles with the duck all over Europe, or the 1435mm network, and in the same time the share of the screw coupler vehicles is decreasing here. We call this process the serial migration, and this is more or less as these wagons are mainly not interacting with other trains. This can be done more or less independently from each other. And second is what we call the core wagon load system. This is completely different traffic. This is traffic mainly interacting with each other. For example, the single wagon network using marshalling yards, but as well as this we consider here wagon group systems. And for example, block trains that are running on the loaded run from the shipper to the receiver, but when then the customer is emptying the wagons and sending them back, maybe he's emptying only 2 or 3 wagons per day and bring it back with a single wagon system. So here we have an interaction with the single wagon system too. And despite the first run is a block train, but then we have a connection to the single wagon system, and this is what we bring here together. And this is why we call it the core wagon load system and not only the single wagon network. This is a bit less than the separable transports. We see here something more than 200,000 wagons all over Europe. And here we need a different approach how to migrate. And the migration approach for this year foresees a very long preparation period where we prepare all the wagons and all the locomotives with everything that we need to install a duct without the duct coupler head itself. So what we do is we bring the wagon to a workshop in a regular maintenance period, for example, not bringing it extra, otherwise we would increase the absence from the customer. We bring it in a regular maintenance scheme to the workshop, and then we retrofit already the spring package, the draft gear, and we put already some empty conduits, for example, for the wiring of the electric equipment and so on. Everything that we can do before the real retrofit of the duct coupler head, we do. And the trick behind it is that the pivot pin between the coupler head and the spring package is the same for the duct as for the current screw coupler. We simply leave this in, but have already the new spring package, so we don't have to lift up the vehicles afterwards. So everything that can be done from underneath is done then, and the rest is rather simple, standardized, and could be done by a mixed team out of old experienced colleagues and some newcomers, maybe from other companies which are helping out here for some months. And in the end, we see here a period that we call Big Bang. And in this Big Bang, this might be a summer break where we have some customers closing their plants, where the transport demand is going down. Then we would like to undertake this Big Bang activities where we bring vehicles to places where we retrofit them. We are not thinking about the existing workshop capacities here. We are discussing currently some of an amount of about 150 what we call pop-up workshops. We bring workshops in tents to bigger sidings where we have a huge amount of empty wagons in these times. Then this might be port areas, industrial zones, or bigger customer sidings. And we tested the procedures in such a pop-up workshop already 6 weeks ago, and we offer there a movie showing what's happening there, but for technical reasons we don't show it here today. So this Big Bang here shall be the answer to the challenge how to migrate a network of more than 200,000 wagons all over Europe in a very short time. And you see, this has to happen in the same moment. So this both has to happen until 2030. And this is quite a challenge. But nevertheless, I'm still optimistic, and I think this can happen. And this can work. I spoke already a lot about wagons. Coming now to locomotives. Locomotives have to be migrated first, of course. You can't pull a train with a digital automatic, and the locomotive has no digital automatic coupler. So the DAC must be on the locomotives first. But on the locomotives, we see several challenges. So the best option would be for the migration period something that we call a hybrid coupler. The hybrid coupler is something that you can see here on the left-hand side. This picture here is taken from colleagues from Switzerland. This is already in use since several years. This is a Scharfenberg coupler head, something similar, comparable to what we are developing currently for the DAC, for the DAC. And here underneath you see the screw coupler, and the buffers are still there. This locomotive can carry either a screw coupler train or and this is not a DAC, it's only an AC, an automatic coupler train. Maybe in the morning the one and in the afternoon the other, and it's easy to lift and to bring it down here, the Scharfenberg coupler. But as you can imagine, this is a weight challenge for the locomotive, and we see in many parts of Europe that this is not possible because the locomotive is already at its weight limit today, and over exceeding the weight limit is not recommended here. So we need other solutions than this. And second is, and this is what we are currently working on in the migration team too. Second challenge is this locomotive type here has the frame stability that you need for a central buffer coupling. So the DAC is a central buffer coupling, and many locomotives, for example, these here shown in the middle, this is a rather new one. They take the incoming longitudinal forces only at the corners of the vehicle frame. So the wagon stability is not strong enough to take incoming forces like this here in the middle of the front of the locomotive frame. And here we see two rather modern locomotives where this challenge has been solved for an SA3 type coupler. These two locomotives are running in north of Sweden and going over to Norway with heavy ore trains. And here you see a front bar, where the coupler is installed, and this additional front bar is one possible solution, but still additional weight. You need some special changes at the locomotive, but this has to be done now, otherwise it won't work. And last but not least, what we never should forget is all those many thousands of siding operators all over Europe. The siding operators are currently maybe receiving in a small siding maybe 3 times a week only 5 wagons. And they are shunting around 5 wagons per day with a very old, maybe 50 years old shunting locomotive. And maybe the book value of this old shunting locomotive, which is not leaving the station anymore and just remaining in the station and used only for shunting demands, maybe the book value is less than the price for such a sophisticated, high-tech hybrid coupler. So to keep the operators of siding services with these old equipment in the market, and you know the whole single wagon system, for example, is depending on all these tiny little stations where the siding services are done. Here we need a low-cost solution for those places where only shunting services are done, and there we need a simple offers For example, such an adapter, this is existing already today. This is no rocket science, but it's not allowed to use this on the long track. Yeah? So we can't bring these adapters to locomotives running on long distance freight trains. So this is quite a challenge, not finished yet. It's not even decided yet to introduce the duct finally. So this has to be done after all the development and testing is completed. But as I mentioned already, I'm optimistic. In the end, we will see maybe in 2030 the buffers and the hook taken away, and then we have a digitized and automated rail freight world on the 40-35 millimeter network in Europe. And we expect that Europe will be then the first continent in the world with a digital automatic coupler being introduced all over the rail freight companies. Currently, we are the last continent with almost no automatic coupler systems in rail freight. Even Africa has some solutions we don't see here in Europe. So I'm optimistic. Feel free to join the European Duct Delivery Program. Share your expertise. You're all welcome. Thanks for having the floor here. I think we still have 2 minutes or so if there is a first question, because I have to leave then in about 8 minutes.
Okay. Thank you very much, dear Lipka, for this very well presentation. And the subject was also interesting for me. I think you will not continue with us, so we can ask some question if anybody has. Is there anybody who asked the question about the subject? Actually, I can ask a question, or I can underline some points. It's a very well system, as I understood. But is the DAC system is compatible with all rolling stocks? Can we apply it to any type of the wagons or locomotives? I'm thinking from the Turkish sides, actually. I mean, is it easy to shift all the fleet to this system, or we can start with a pilot area? And what about the feasibility? Actually, you gave some information about those, but maybe you want to make a brief information extra.
So the idea behind it is by using the Scharfenberg coupler design to have the broadest compatibility to other systems. For example, in many passenger trains we see the Scharfenberg design too. So, for example, in case of emergency, you could pull a passenger train then still with a freight locomotive. So there is a compatibility. You were asking about feasibility. The business case behind it is that without any public funding, the whole work is almost not feasible. Only on a very, very long run, but no company would do this, because the management will be retired in most cases before they see the benefit of this investment. So therefore we need a decent public support by subsidizing the whole project here. And as we see currently with Green Deal funds in the European Union, for example, and the backwind for rail freight in terms of sustainability, we are here still, the signs are currently rather promising that there can be done a solution to make this whole thing more feasible. I see a question by somebody wrote a question in the chat.
Yes, at the chat box. If you state that the target date is 2030, this means the works need to start in 2024.
This is currently the plan, beginning with making vehicles duct ready. So this preparation with the spring package and so on that I mentioned, you can do already, even, for example, if the final test certificate for the coupler head is not signed until then. So what we can do is, once we decided we want to have the duct, we can start with making vehicles duct ready, and this preparatory period can start then already in 2024. Given that the spring packages and everything that should be installed in the duct ready process is tested and confirmed until then. But this is currently the plan.
Okay. Any more questions? Okay. I would like to say thank you for this well presentation, and we will continue with the second presentation. If you want to say anything else.
Thank you very much for
Okay.
being your guest here today. It was a pleasure to me, and I'm always happy when I see that people are focusing on digitization, on automation for a more than almost 200 years old traffic system, and this will help us to come to a brighter future. Thanks to all of you, and have a nice day.
Thank you very much. Okay, now we can pass to the second presentation. We are on time. We are turning to the Aselsan. Actually, Can Pehlivan would join to this presentation, but instead of him, Özgür Tırnakçı will make a presentation. The title is Automatic Train Control and Safety Approach in CBTC Projects, Communication-Based Train Control Projects. Dear Tırnakçı, if your presentation is ready, you can share your screen and start your presentation.
Can you see my
Yes.
screen at the moment?
No
Okay.
problem.
Okay, good morning and good evening, ladies and gentlemen, and dear chairman. Let me thank you for attending the webinar. My name is Özgür Tırnakçı, and I am the project manager at Aselsan Rail Systems Department. Actually, as Mr. Chairman said, it would be my manager, Mr. Can Pehlivan, who would be attending the meeting, but at the very last second, he had to attend another meeting, so I'll try to take over. So today I will try to explain automatic train control and safety approach at Aselsan for our communication-based train control projects. So I would like to start my presentation with a question. What's the difference between a warship and a metro system? I have started working in the railway sector after spending more than 2 decades in naval projects. I have actively took part in many naval warship projects since 1999. Yet these ships have not been involved in any actual combats, luckily, but only in exercises. Hope they won't in the future. In contrast, metro systems have to operate and carry passengers in the conditions they were actually designed for. Therefore, they have to meet higher level of safety criterion, among many others, while the warships survive more severe environmental conditions. My presentation is divided into 3 parts. First, I will give you brief information about CBTC. Next, I will talk about safety. And finally, I will look at the ATC for CBTC projects. Let's start with the CBTC. So communication-based train control is a railway signal system that makes use of uninterrupted, high-capacity, bidirectional communication between the train and track equipment for traffic management and infrastructure control. By means of CBTC systems, the position of a train is known more accurately than the traditional signaling system. This results in a more efficient and safe way to manage railway traffic. Metros and other railway systems are able to improve headways while maintaining or even improving safety. Let's have a close look at the system philosophy. So the train B calculates its position and speed with an odometer system consisting of tachometers, accelerometers, and Doppler radar installed on board. The uncertainty in position error is reset to 0 at the passing of each balise installed on track. So the train B transmits its instantaneous position to the wayside ATC systems over the data communication network, or the DCN, at each cycle time in secure channel via mobile data radio. So the wayside ATC system determines the last point where the trains can move according to the movement authorization limit. The wayside ATC system transmits the movement authorization limit and the related line block speed limit to the trains in each cycle time via the Wi-Fi antenna. The onboard ATC system, including automatic train protection and automatic train operation, continues to calculate the safe brake curve according to the instantaneous position, moving authority, and speed of the train. Automation effectively solves the increasing demand for passengers transport, safety issues, human error, and increasing congestion. The use of technologies such as high-speed and high-capacity internet technology, advanced communication solutions, artificial intelligence, and Internet of Things increase the development and reliability of autonomous vehicles more and more every day. If we look at the benefits of autonomous rail systems, there are three major advantages: cost, efficiency, and safety. My next point is safety. On September 2018, London Underground Jubilee Line train traveled between Finchley Road and West Hampstead stations with doors open. The train, with approximately 30 passengers on board, So the train, with approximately 30 passengers on board, reached a maximum speed of 62 kilometers per hour during the 56-second journey between these stations. Luckily, no one fell out of the train and nobody was injured. Unfortunately, there have been injuries and fatal accidents in the past. Because of this, safety is the most important issue in the railway sector. As a summary, in CBTC application, safety always comes first, and all staff, operators, and system suppliers are responsible for the achievement of the required performance, safety, and reliability of the system. The operating organization identifies system-level hazards, acceptable risks for them, and safety objectives for the operation. The system provider's responsibilities are reducing risks to acceptable levels, proof by testing and analysis that acceptable risks have been reached. As the CBTC system is a safety critical application, its safety integrity level, or SIL, requirement has to be the highest SIL 4 in the railway industry. In most cases, both wayside ATC and ATP subsystems are designed to SIL 4, whilst the ATS and ATO subsystems are assigned to SIL 2. Okay. Okay. So, safety policies are given on this slide. So, conformity with the requirements, these are given in the SEGELEC EN standards, and prevent fatalities and serious injuries, and reduce the frequency and impact of hazards. Okay, let me check my notes so that I can continue. Okay, so this is the safety organization in Aselsan at the moment. So we have to redesign, let's say, and safety organization in our company in order to perform the activities that we have been doing at the moment. So this is a new actual reorganization for us. So we have an independent safety assessment or assessor here in our companies, here in our projects. So in our project right now, it is RINA of Italy, and we have a project team and a safety team, which is also consisting of engineering and design, manufacturing, system integration, and system validation. On the right, on the left-hand side, you can see our project team, how we are performing these activities in Aselsan in a more detailed way. So the automatic train control So this is the ATC and the main block diagram of our CBTC system. The CBTC system is mainly composed of the three subsystems here, and the first one is the onboard ATC or onboard ATS ATC system, so which is composed of two subsystems, which is onboard ATO, onboard ATP, onboard train operation, and the onboard train automatic train protection. So an automatic train control system integrates all vital and non-vital functions that guarantee the safe operation of trains. It comprises of three subsystems. So these are mainly the ATS, ATU, and ATP. And these subsystems together with a full interlocking system perform the following actions, which are signaling, automatic train protection, traffic management, and automatic train control, which also includes automatic train operation functions. So safety integrity combines two basic concepts: integrity against systematic failures and integrity against random failures. The first one represents those specification failures, traceability, design, manufacturing, and maintenance caused by a failure or incorrect human process. In contrast, the second one occurs randomly due to mechanical or electronic equipment failures or aging process or wear. Taking into account these two types of failures, the concept of safety integrity can be defined as the capacity or probability of a system to perform safety functions associated with its target, usually under specific conditions and in an operating environment being predefined and for a certain period of time. In short, its ability to operate correctly without any of these failures will occur. Safety integrity is measured in hours, and its value associated with probability of occurrence. So for railway systems, safety integrity level is defined in SEGEREC standards EN 5126, EN 5128, and EN 5129. So I'd like to share some points. I'd like to share some points that we consider as the standards required in the design of CBTC system. These are top-down design methods, clear documents and traceability, systematic V processes, traceable change and configuration management in hardware and software design, of course. So they are composite fail safe design, sensor fusion, redundant system architecture, maintenance friendliness, low mean time to repair MTTR with modular design, self-diagnostic, and hardware diversity. Also, there are additional factors like the safety critical components used must be SIL4 certified, such as the BALIS, BTM, Relay, and Safe Computer. Use of SIL4.
Can you hear me?
Yes.
While reading some certain sentences, can you be slower because of the translation?
Sorry.
Warn me. So if you can be slower, it will be better.
I will, of course.
Thank you.
Thank you for the warning, sir. So, use of SIL4 safe protocol in safety critical functions to avoid creating cybersecurity vulnerabilities. An independent safety assessment after the control and examination of each stage of the design by the independent quality department taken into account. I have a small problem with this. Okay. Okay, so the ATC, autonomous operation, supports safety functions, determinism, accuracy, lower rate, and progressive improvement. Also, it provides adaptive planning and high capacity. So let me just give you some basic information about Aselsan CBTC projects which are underway at the moment. So Aselsan CBTC system is being deployed at Gayrettepe Istanbul Airport and Istanbul Airport Halkalı Metro Line projects. Actually, as you can see on the slide, it is the continuity of the previous line. So the details of these projects are on the slide. Sorry, they are written in Turkish, but I'll try to translate into English. So it is governed by the Ministry of Transportation. So the total length of the first line, which is in orange, so it is 36.6 kilometers. And the operation speed is 120 a bit higher speed than the conventional metro lines, which are operating at 80 kilometers per hour, as you know. So the total number of stations is 9, and total number of trains is 20 sets. So it's going to be, at the very end, will be GO 4, which is totally driverless, and the safety will be again SIL 4. So it is hot redundant, and also two geographically different positions, and for the control of the whole operation. There will be only one depot, which is just after the cargo terminal station, which is, as you can see here. So the depot line will be somewhere here. So this orange line is called the Gayrettepe Istanbul Airport Metro line, and the one which is in red is also again governed by the Ministry of Transportation. The total length is 32.4 kilometers. Again, the speed is the same. There will be 7 stations, and there will be again additional 24 sets of trains. Again, it's going to be GO 4 at the very end. And this is the headway the system is designed for, which is 180 seconds at the moment. So the line is going to be opened in a very short period of time, probably in 2 to 3 months of time. And it will start with 10 trains, including also the spare ones. And of course, it's not going to be GO 4 because the trains are not driverless, but procured from China with the one with the driver. So it's going to be GO 4 at the moment. And then with the procurement of the new ones, it's going to be upgraded to GO 4. So the good thing with our system is we do not use any additional trackside equipment in order to upgrade the system from GO 1 or to GO 4. It is all done by software means. So we will going to upgrade this software to GO 4 as soon as the trains are procured, and we will of course perform the test activities related. So I think all the people coming to Istanbul will enjoy our line in the very short period of time. So the second one right now we are which is underway is again the Gebze Darıca Metro Line project. It is again governed by the Ministry of Transportation. So the total length is 15.4 kilometers, and the conventional speed here is 80 kilometers per hour. So there will be 11 stations, and the total number of cars is 28. So each set consists of 4 cars. And by the way, these trains are manufactured by a Turkish company. So this line is going to be 100% Turkish line, where the contractor is Turkish, where the signal company is Turkish, and the trains are again Turkish. So these trains are coming directly from the company as driverless. So this one probably will be the first one with GO 4 capability. Probably it will be sooner than the other line, because the cars are going to be ready in 2023. So as Aselsan, we are going to deploy, hopefully, our GO 4 system into this one next year, or maybe in 2024, due to the construction and other works. So the safety is again SIL 4, and again it is going to be fully hot redundant, and again there will be 2 geographically different places in order to achieve the hot redundancy. So this concludes my presentation, and let me thank you again for your patience, and I hope you enjoyed the presentation. If you have any questions, please feel free to ask.
Okay. Thank you, dear Tarakçı. It was a good presentation and good work. I think there will be some questions, but because of the usage of the time, maybe we can pass to the next presentation. But at the end of all presentations, we will be making a discussion hour. So I want to pass to the third presentation, and thank you very much for your presentation.
Thank you very much, Mr. Chairman.
Yes. The third presentation presenter is the Professor Klaus Werner Schmidt, Electrical and Electronics Engineering in the Middle East Technical University. Hello, Mr. Schmidt.
Hello.
Hello. And the title of the presentation is Application of Connected and Autonomous Vehicle Technologies for Autonomous Trains. You have 20 minutes. We are waiting for your presentation. Thank you.
Okay, thank you, dear moderator. I also would want to thank the UIC, the International Railway Research Board, and specifically the representatives of TCDD, the state railways of the Republic of Turkey, for organizing this webinar and also for inviting me to this webinar. I will talk about application of connected and autonomous vehicle technologies for autonomous trains. And let me first give you some short overview of what we are doing and why what we are doing is also relevant in the end for autonomous trains. We have a laboratory called Active Lab, and we are dealing with topics like autonomous driving applications, sensor data processing, model-based control, simulation, real-time embedded systems. We have in-vehicle communication, vehicle-to-everything communication, and specifically also we have some work on the train communication network, TCN. Okay, so these are all topics that are both related to autonomous driving if you talk about cars, buses, trucks, so vehicles on the road, but also they are related to autonomous trains, as I will try to explain in this presentation. So let me start with a short motivation of why autonomous trains are going to be important in the future. There's several bullet points, like you want to improve the overall safety of the railway system, you want to increase the existing capacity, you want to lower operational costs, improve service reliability, improve the energy efficiency. And when I looked for material for this presentation and I found these items, I had to say this looks very similar, sounds very similar to what is the motivation for autonomous road vehicles. Okay, and now, because of this connection, the objective of this presentation will be, on the one hand, to identify certain common points between connected and autonomous vehicles and autonomous trains for a possible technology transfer, because there's already a lot of technology around for autonomous vehicles. And on the other hand, to also clarify certain differences between these two applications of autonomous systems, such that you don't go in the wrong direction. So let me start with the outline of the presentation. After this short motivation, I will first recall the autonomy levels for autonomous trains. I will talk about some architectural considerations. Then I will introduce several important sensor technologies, some correspondences between autonomous train and autonomous vehicle applications. And in the end, I will give a summary. So let me start with the classification of autonomous trains depending on the grade of automation. Here you can see this kind of standard matrix where you have the grade of automation in the rows, and there are different features that you can see in the columns of this matrix. Okay, so for example, the first grade of automation means that still the train is driven by a driver, but the train protection is sort of autonomous, at least partially. In the second level, you would have autonomous train protection, automatic train protection, and also you would automate the train operation with a driver, at least partially for some of the tasks. If you talk about level 3, then you would say we have driverless train automation, and completely unattended train operation would be in this grade of automation number 4. Now, the interesting thing is there's this very similar list of levels of automation. It's published by the Society of Automotive Engineers, which are called the levels of automation for autonomous vehicles. So they're very similar to this. There's just one minor difference, that if you're talking about train systems, the players are not only the driver and the potentially autonomous train, but one more player would be the attendant, which has to, for example, take care of the door closure and also what happens in an event of disruption. Okay, so what you can say is, if you look at the correspondence from this high level between connected and autonomous vehicles and autonomous trains, then most of these considerations about levels of autonomy, they run in parallel, but whatever is related to opening, closure of doors, and what is related to the attendant in a train system, these levels, of course, they don't have a correspondence when you talk about this correspondence between autonomous vehicles and autonomous trains. Okay, so in any case, for the remaining boxes in this matrix, the connected and autonomous vehicle technologies are applicable. As a second point, I want to have some architectural considerations. By architecture, I mean how the vehicle is connected to the hardware and software that is used in order to make the vehicle autonomous. Now here I'm starting from the road vehicle, and what you would have is, on the one hand, the vehicle platform itself, the physical vehicle, and on the other hand, you have some software which is running on some computing device which is supposed to control the vehicle. And as an interface between these two, on the one hand, to get data from the vehicle, you have sensors like camera, radar, LiDAR, GPS, inertial measurement unit, or vehicle-to-everything communication. And on the other hand, you have actuators in order to control the vehicle. Okay, so steering, throttle, brake, and gear are the relevant actuators for a road vehicle. Now, if you look at this kind of picture, again, what you can say is that all the sensors that you see here on the left-hand side, they are also relevant for autonomous trains. On the other hand, algorithms that are related to perception, which means learning something about the state of the environment, and also algorithms related to planning will also be related to the operation of autonomous trains. So what you could say is solutions from connected and autonomous vehicles that are in this domain, that belong to these sub-modules, I can say, they can also be applied to train systems. On the other hand, if you look at the specific solutions that are needed for trains, for example, if you want to do the longitudinal control of a train, which has completely different dynamics than an autonomous vehicle, then you will need specific solutions. Okay, but all these more, I would say, high-level tasks, planning tasks, perception tasks, they can be transferred from autonomous vehicles to autonomous trains. Now, we can go into a little bit more detail, just looking at different sensors and example applications. Okay, for sensors, relevant sensors are cameras. Cameras can provide an up to 360-degree field of view around the vehicle. They can be used for different applications, such as object detection. For connected or autonomous vehicles, they would also be used for lane detection. There are LiDAR, light detection and ranging sensors. Again, these kind of sensors, they scan the overall environment and they generate a so-called LiDAR point cloud of the environment. And this gives us information about the shape and the depth of the environment. Okay, so at what distance will you see an object? And LiDARs can also be used for object detection, and they're also used for a task that is called localization, which means finding out where the vehicle is on the road, at which position. Other sensors that are also frequently used in autonomous vehicles are GPS to get a more coarse location information, and also inertial measurement units, which tell something about the acceleration, rotational velocities of the vehicle. And what is also frequently considered as a sensor in connected and autonomous vehicle applications is the V2X communication, so vehicle to everything communication. Now, after this list of sensors, let us look at some examples of use cases for these sensors and how these use cases relate between autonomous vehicles and autonomous trains. Let's first look at the vision-based object detection based on camera sensors. So what you use commonly as the methods for this object detection is different architectures of deep neural networks. Okay, this is both applicable for connected autonomous vehicles as well as autonomous trains. Okay, what is also similar between these different domains is the objects. What kind of objects would you have? You would want to detect cars, other trains, you would want to detect people, bicycles, and so on. And very important, what is also a common point is the real-time requirements for these applications. Okay, so real-time is important for connected autonomous vehicles as well as autonomous trains. Of course, there are some differences. If you look at vision-based object detection, what is one difference is the relevant distance. For a train, you have to look in the future more. The environment for a train, you won't drive in an urban environment, but you're going to drive on the track of the train. So you will see some different environment, maybe some railroad crossings, but this is the main possible intersection. And you will also have different scenarios. Okay, so what I can say when you look at vision-based object detection is that you can use similar methods if you want to apply this vision-based object detection to connected autonomous vehicles and autonomous trains, but we're going to use different training and test data just because the scenarios and environments will be different. Okay, but the technology learned from connected autonomous vehicles, it can be transferred to the trains. Let's look at another example, which is LiDAR localization. For LiDAR localization, what you want to do is you first generate a map of the environment. So there's a mapping stage. And then when driving on the road, you use this map, you compare the map and the measurements from a LiDAR sensor. And by this comparison, you can just pinpoint where the vehicle is on the road. Okay, so this is called 3D registration. These are algorithms to generate maps. And then from these maps, you can find the location of the vehicle on the road. Now, you want to do something similar for trains. For example, you would want to localize the train in a train station. Okay, so the sensor technology for such an application will be very similar. It will be the same. The real-time requirements that you have to fulfill will also be similar. Of course, again, the environments will be different, and there will also be some differences regarding the vehicle motion. Okay, for a car, it is the case that the car will be able to have very, very tight turns, whereas trains, they drive on very smoothly curved tracks. Okay, so this is one difference, and as a result, the cars, they will also have some motion in the roll and pitch direction, which the trains normally don't have that much. Okay, so there are some fine differences in the vehicle motion, which have an effect on the application of these technologies. But in any case, between cars and trains, you can apply similar methods, but with some slightly different features. Okay, so again, technology transfer is possible. If you look at vision and GPS-based localization. So again, localization means you want to find the location of your vehicle on some map, for example. Then for connected autonomous vehicles, there are algorithms to perform lane detection. And this is very similar to algorithms for track detection that you can use for autonomous trains, as you see on the right-hand side. Okay, so this is, for example, important when you want to combine this with object detection to identify if some passenger is crossing the track in front of you. Okay, so here again, the same methods can be applied. And similar things can be said for GPS-based localization. Okay, what you do for connected autonomous vehicles is you do sensor fusion together with motion data. So you take the absolute position information from a GPS satellite, multiple GPS satellites, and you fuse this information with the information you get from the vehicle sensors like velocity, turning, and so on. Same thing is done for autonomous trains. So sensor fusion is done with inertial navigation data. Again, the same methods and very similar algorithms can be applied with the similar constraints like real-time constraints that have to be obeyed. Okay, let me also talk about one more example, the sensor fusion of LiDAR and camera, because in autonomous vehicles, sensors are normally not used on their own. Normally, data from different sensors are combined to get a better picture of the environment. For example, if you look at LiDAR and camera, then cameras have the advantage that they have a high resolution and they can distinguish colors. Okay, but cameras are unfortunately sensitive to light conditions and they don't support easy distance measurement. On the other hand, LiDAR sensors, if you buy a good one, they have a 360-degree field of view. They allow distance measurement, but they cannot distinguish colors, and it's difficult to use them for object classification. Okay, so distinguish, for example, cars and buses, or buses and trucks. Okay, so what you can do is, applying sensor fusion, you can compensate for the disadvantages of the different technologies and hence improve robustness and accuracy of your environment perception. And the same applies for autonomous vehicles and autonomous trains. Okay, so again, in the area of sensor fusion, this technology transfer is directly possible. Finally, one more point that was also mentioned in the previous presentations. An important point is vehicle to environment or vehicle to everything communication. For connected and autonomous vehicles, this is done using onboard units and roadside units. And there are special standards for that purpose. For example, there's a standard called dedicated short range communication for that purpose. And there are also special frequencies allocated for that. And this V2X communication currently is used for safety warnings, for traffic management, and also in the future, it will be used for coordination of vehicle motion. If you look at autonomous trains, then here we already have the communication-based train control. And as we saw in the previous presentation, it is, for example, used for moving block signaling. Okay, so here we have different technologies, and also we have different applications. Okay, so a technology transfer in this area doesn't seem to be very beneficial from my point of view. However, if you look at the intersection between the two worlds, okay, so trains and vehicles, they are not living in completely disjoint universes, but they come together at certain points, like railway crossings. So at railway crossings, there will be a need for technologies like this. On the one hand, the connected autonomous vehicles, they communicate with roadside units, which have then the information about what's going on the road. On the other hand, the autonomous trains communicate with GSM, with radio basically, in the communication-based train control system. Okay, so now these two worlds have to be connected. So there has to be an integration between these two worlds, meaning that on the one hand, we have to provide approaching train information to the RSUs, such that this information can be given to vehicles. On the other hand, we have to provide connected autonomous vehicle traffic information to the train communication system, such that the train can react if necessary. Okay, so there will be a need for intelligent railway crossings that combine the two worlds. Okay, as a final important step, I want to mention that not everything is done in real life. So what is a very important tool is simulation in the development of autonomous system applications. Okay, this is true for autonomous vehicles. It's also true for autonomous trains. And there are different levels for simulation. There's model in the loop, then the system, the vehicle is modeled, and also the software code is modeled, and they're simulated together on a single PC. There's software in the loop simulation. Here the system is modeled, but you run the real software code in a PC. There's hardware in the loop simulation, where the system model is still simulated, but now it is simulated in real time, and it is connected to the real computing hardware, which is running the autonomous functions, the autonomous software. Okay, so for vehicles, for connected autonomous vehicles, there are whole tool chains that implement these different levels of simulation. And I believe that also for trains, such tool chains will be very important for the development of autonomous trains. Okay, so this is an important point to focus on, and I saw already that some simulation tools are now popping up. So to summarize the presentation, What I talked about is, first of all, some corresponding problems between the different domains of connected autonomous vehicles and autonomous trains. For example, we identified object detection, localization, safety warnings and measurements, and also traffic management. I also identified several corresponding technologies and in which way technology transfer is possible, related to sensors and sensor data processing, related to sensor fusion, related to the integration of CBTC and the vehicle-to-everything communication system. And I also pointed out the importance of simulation-based testing on different levels for the development of autonomous systems. So at this point, I would like to thank you for your attention, and questions I think will be handled later.
Yes, dear Professor, thank you very much for your presentation, very informative presentation. We saw a good comparison between the road transportation and rail transportation in terms of the autonomy. I will have some questions, but yes, you are right. We should go to coffee break now for 20 minutes again, and then we will listen to more presentations. Then we will take the questions totally. And again, I want to say thank you for your presentation. Now we can, thank you. We can give the break, I think, Mr. Atila, right? We are not leaving the session. We are just closing the microphones and cameras. And then 20 minutes later, we will be here, right?
You are right, Mr. TUZKAYA.
Okay, okay. See you then. Bye, everyone. Problem. Okay, recording has started. Okay, we have finished 3 presentations. Now we will continue with the dear Mr. Mehmet Demir from Metro Istanbul Consultancy Service Director. And the name of the presentation is Conversion of Istanbul M1 Metro Line from Grade of Automation 1 to 4. Yes, we are waiting for your presentation, Mr. Mehmet. You have 20 minutes.
Okay, hello, my name is Mehmet Demir. I am working as a consultancy service director in Metro Istanbul. I think my screen is shown. Is it correct?
Yours, we see the small slides, so maybe you can exchange the or shift the screen. If you are using 2 screens.
Yes. Right now?
It's didn't change.
Oh, just a second. I think now okay. Okay. I want to explain the conversion of Istanbul M1 metro line from grade of automation 1 to grade of automation 4. I first talk about the Metro Istanbul. We are the company of the Istanbul Metropolitan Municipality, and we are Turkey's the biggest metro, light rail, tram, funicular, and cable cars operation company. In transportation mode in Istanbul, 25% of the passengers use the railway system. This is very important for Istanbul, because Istanbul is, as you know, most of people know, there is a big traffic problem in here. So rail system using is increasing thanks to railway systems. And some statistics about my company. We are about 100 passenger information systems. We are about 1,000 vehicles, rolling stocks. We have more than 1,500 escalators, etc. As I said, we are Turkey's the biggest operation company about metro and tram operation company. And all full station is 100% accessibility for handicapped people. This is our Istanbul's right now network map. Except the black one, all system is operated and maintenance by us. The black one is operated by TCDD. The first flash is using our M5 line. This is the Turkey's first fully driverless metro line. And this is the Turkey's second fully driverless metro line. Also Europe's first driverless metro line. And we talk about that red line. As you see, it's start from Yenikapı and go to the Kirazlı and Atatürk Airport. We talk about that red line. And this is our readership. M1 line is its daily passengers about 500,000 passengers. So it's the close to highest it's our highest metro line. And by the way, this metro line is it's our first metro line, and it's about 34 years old. We will talk about that metro line. As I said, it's start from Yenikapı to go to Kirazlı and go to Havalimanı. Also, that line is under construction there is an extension from Kirazlı to Halkalı. It's about 10 kilometers and 9 stations. All of them is underground. The exist metro line is, there is we said M1A and M1B. M1A is the 18 stations. 11 is street level, 7 is underground. And the B side is 1 is street level, 4 is underground. Totally, it's 36 kilometers and 32 stations. Why we need the convert the system? The 9 station extensions of M1 metro line will bring integration with other lines and increase number of passengers using M1 line. Also, passenger exchange feasibility report shows that more than 600,000 daily usage and our hourly passengers close to 40,000 passengers. And also, right now we have low operation capacity, high passenger demand, high headway time, old and insufficient signaling system. As I said, this system is about 34 years old, and old and insufficient trains. Also, our train is about 34 years old. This signal system is Bombardier Stofilo 250. It's a very old system, and most of equipment is end of life. As you see the screen, it's very crowded, especially in peak times. Most people can't use the train, wait for second, third, or fourth train for using that line. It's really our most crowded line right now, one of the most crowded line. That's why we need to convert. We're supposed to, after the conversation, right now the automation, as I said, the grade of automation 1. At the end of it will be grade of automation 4. Right now our headway is about 3 minutes. After the conversion, it returned 19 seconds. Our peak hour capacity right now is 18,000 passengers. After conversion, it increased about double size. And right now we use the driver, and it is, as I said, grade of automation 1. After the conversion, it will change the automatic train operation. Right now we don't use platform screen door. After the conversion, we will use the PST also. This is the generic schematic. Most of railway person know that schematics. In M1 line, we use the grade of automation 1, so we just use ATP with driver, stopping, going on, door close, door openers. Also, all these procedures done by the driver. But at the end of when we finish our project, it's convert totally fully automation, fully driverless mode. So the type of train operation return the UTO, train motion, train stopping, door close, door open, all then will return the automatical mode. This is the right now our passenger station length vehicles number. Extension line, it will be like this schematic. Our daily passenger we want to will be about 600,000, and our station will be 33 station. You see the schematic. That's our ambitions. At the end of the project, we want to see the right side numbers. This is the generic CBTC grade of automation pictures. At the end of course, there will be operation control center, systems room. In the platform, we will use the platform screen doors, and train use onboard system with hot redundant systems. And we will change the wayside systems, wayside equipment. The conversion of train side, hot standby redundant onboard ATP we will change. We will change hot standby redundant onboard ATO equipment. Of course, onboard control and communication systems, because there is no driver. And redundant tachometers, conversion of radar, conversion of ballast readers. The system will be like the schematic as you saw at the top of the presentation, down of the presentation. We use propulsion of and brake control, odometers, etc. And again, what changed in train side? New trains with TCMS support redundant onboard ATC, derailment equipment, obstacle detection systems we will set up, intercom system we will set up, onboard CCTV systems, train SCADA system, passenger announcement systems, and OCS Wi-Fi network system and passenger information system will change, we convert, of course. And what changed in wayside? We will convert the wayside ATP systems, wayside automatic train operation systems for UTO metro operation, conversion of point machine, of course they will change, conversion of ballast, platform emergency stop button for unauthorized access to track, PST systems and Wi-Fi communication systems for OCS also set up in wayside too. And of course, we need to convert of the OCC side too. Conversion of signaling workstations, OCC workstation setup, installation new video wall systems and maintenance workstations, rage and wait sub buttons for emergency situation. At the end of the project, we planned the system will like with this. In the operation control room ATS systems, there are redundant ATS servers, and operation control room also includes some workstation, and they communicate with wayside systems for ATP and ATO. We use the radio access point, and of course there will be station room which includes the object controller for switch machines, emergency stop button. Also, we can say platform emergency stop button and platform screen doors. And of course, inside the train, there will be hot redundant ATC onboard equipment, and also wayside it includes the tech for positioning of the train. Our target is like these systems. Okay, thank you so much for listening to me. If there are any questions, Of course, I want to explain.
Thank you very much, Mr. Mehmet Demir. We have some times, but let's not break the rules, and we have only one presentation. After we listen maybe we can get the questions together, all of them. So thank you very much for your presentation.
Okay, thank you so much.
Okay, the last presentation of today will come from dear Mr. Shigeto Hiraguri. He is the Deputy General Director, Research and Development Promotion Division. And the title of the presentation is The Current State of ATO in Japan and the Newly Developed Intermittent Type ATP-Based ATO Systems. Okay, you have 20 minutes again, Mr. Hiraguri. Okay. Can you open your microphone? We can't hear.
Oh, sorry.
Okay, we can hear.
Okay, can you see my presentation?
Yes, no problem.
Okay, so thank you, Chairman. Good afternoon, and everyone. I am Shigeto Hiraguri, Railway Technical Research Institute, Japan. I'm honored to have an opportunity introducing current situation of automatic train operation systems in Japan. Okay. Oh, sorry. Okay. So my presentation is divided into two parts. In chapter 1, I will overview of current state and development of automatic train operation system, ATO, for the future. In chapter 2, I will introduce Japanese new concept of grade of automated train operation and a unique challenge by Kyushu Railway Company. They developed and they are continuing demonstration operation of newly developed ATO system that is based on intermittent type ATP. I think such ATO system is the first case in the world. So I'd like to start my presentation. Oh, sorry. This chart has already indicated other presenters. So generally, when we talk about ATO, we assume GOA 2, 3, and 4. I also introduce outline of GOA 2, 3, and 4 in Japan. In Japan, ATO systems are operated in about 40 lines, more than 700 kilometers. 75% of ATO systems are GOA 2, and the rate of GOA 3 is approx 2%. GOA 4 is approx 20%. This trend of percentages may be almost same as in other countries. One of the preconditions for introducing ATO is that continuous type of ATP is introduced. I think this precondition is common in other countries. In Japan, this type of ATP is called automatic train control, ATC. And second precondition is that the line is physically separated from outside by dedicated elevated track, underground tracks, and platform screens. Recently, platform screen doors are being installed mainly in urban area. However, operated GOA4 systems are currently limited to such as AZT automated guided transit system line. In other words, GOA4 hasn't yet been applied to subway and so on. This is a different status from other countries. So this is an example of the GOA2 system, which is installed in Marunouchi line operated by Tokyo Metro company. Outlines of the line are as indicated this descriptions. In this system, ATO works under the protection of ATC. As indicated in this picture, the cab signal is installed when the driver pushes this white button. The train departs from the station. As indicated in these pictures, partial height platform screen doors are installed, and this picture indicates beacons of onboard and ground that transmits door open and close command. This is another example of GOA2 system, which is installed in Tsukuba Express line operated by Metropolitan Intercity Railway Company. This line connects between central Tokyo and suburbs of the northeast of Tokyo, and the maximum speed is over 100 kilometers. As indicated in pictures, basic system configuration is almost same as Marunouchi line. This is an example of GOA4 system, Yurikamome line, which runs in seaside area of Tokyo metropolitan area. So as indicated in these pictures, this is AGT automated guided transit system. The train runs guideways. Train runs on guideways, and it is driven by rubber tires. So I'd like to summarize introduction current status of ATO in Japan. As I mentioned, at present, GOA4 system isn't applied to conventional lines. However, in 1981, first GOA4 system in the world was installed in port liner in Kobe. So actually, Japan has a long record of operation of GOA4 system. In about 40 lines, ATO systems are operated mainly in subway, GOA2, and AGT GOA4. Furthermore, ATO hasn't yet been applied to general conventional lines. So in my presentation, general conventional line assumes such lines where level crossing exists, platform screen door isn't installed, and so on. On the other hand, in other countries, GOA2 system is applied not only to subway, but also to urban railway. And GOA3 or GOA4 system is used is more than 100 lines other than AGT line. So in Japan, applying ATO, especially GOA3 or 4 to general line hasn't been considered realistic. However, recently, that situation is changing, and railway operators are beginning to take a concrete interest in it. To apply GOA3 or 4 to general lines, it is required to apply or develop other solutions to secure equal or better safety of ATO system applied to AZT. These are examples of issues. Therefore, the group study of Ministry of Land, Infrastructure, Transport and Tourism discussed these issues by last March. Of course, experts and operators participated in discussion in that study group. So I'd like to introduce unique idea in Japan. New concept ATO tentatively named GOA 2.5 is being discussed and developed. In Japan, railway operators focus on ATO as the solution not only to sophisticated operation, but also to reduce train operation costs to maintain rural lines. From this point of view, ATO based on intermittent type ATP is being developed. And in Japan, ATP is classified into automatic train control ATC and automatic train stop system ATS. Please notice that in Japan, ATS doesn't mean automatic train supervision. So, and ATC is based on continuous transmission of signal information using rail or radio, and in most ATC, cab signal is equipped. On the other hand, ATS is a system to back up a driver so that the train doesn't pass the stop signal. There are many types of variation in ATS. In the basic type, the train receives control command from the ground beacons intermittently. In current ministerial ordinance of Japan, ATO GOS 3 or 4 is assumed to be performed under protection of ATC. However, ATS accounts over 90% of general conventional lines. Moreover, introducing ATC would entail a huge amount of investment cost to replace ATS. Therefore, GOA 2.5, which is based on existing ATS, is being proposed and developed as a solution to realize ATO in general conventional lines, especially in rural lines. This table indicates the concept of GOA 2.5. Of course, GOA 2.5 isn't defined in any kind of standards. This name is tentatively used only in Japan. Most unique feature of GOA 2.5 is that the staff works at the cab, but he or she doesn't have driver's license. The staff is in charge of the staff is in charge of roles such as emergency stop operation and evacuation guidance for passengers in emergencies. So I'd like to move to chapter 2 to introduce the unique project of developing GOA 2.5. There may be various ways to realize GOA 2.5. For example, JR Kyushu Railway Company is now developing one realization method, which is based on ATS intermittent type of ATP. We, RTRI, is supporting technically their challenges. Important purpose of JR Kyushu's ATO is to reduce the train operation cost, especially in rural lines. At the beginning of the project, JR Kyushu requires that using existing ATS type DK, So this type of ATS was developed by RTRI, and it was installed from 2011. ATS DK is intermittent type ATP, but it has possibility to be the basis of ATO because it's onboard unit based on fail-safe architecture, and it can detect train position and check the train speed continuously. This is outline of ATS DK's function. Ground beacons transmit digital message to the onboard unit. Onboard unit have the database of line profile, and it calculates running distance using outputs from a tachymeter. So the train detects its position continuously. Onboard database has information of speed limit due to curve and so on, and the onboard unit calculates a permissible speed profile. If the train receives the distance to the stop signal from the ground beacon, it calculates permissible speed profile. If train speed exists the profile speed, ATS-DK outputs command for emergency brake. In other words, ATS-DK is intermittent type ATP, but it realizes continuous train control. However, ATS is a backup system in Japan, and the driver controls train primarily. So ATS-DK doesn't check the speed down to 0 km/h for a flexibility of train operation. On the other hand, to realize ATO, the system should check the speed down to 0 km/h, as indicated first row. Okay, and another difference from ATC-based system is indicated second row. According to this point, it is required to develop the method to departure control from stopped state at the station and to response to sudden signal change to stop aspect. Furthermore, because the train also runs in non-ATO line where the train is operated manually, same as conventional, it is required that behavior of ATS-DK in such lines shouldn't be changed from current one. Therefore, it is key issue to develop a new system that complementing ATS-DK's function without changing its behavior in conventional manual operated line. This is the configuration of GOA 2.5 system, which is being developed by JR Kyushu. They solved the problem by applying fail-safe unit to ATO. This is indicated in this picture as FS ATO, and it performs a part of safety-related function. FS-ATO communication between ATS-DK's unit and calculates running speed indicated as green line. So this function equivalent to driver's operation. And FS-ATO unit calculates permissible speed profile indicated as blue curves. This function equivalent to conventional ATC function. So permissible speed profile by ATS-DK indicated as red curve is as backup, and its shape isn't changed from conventional one. As measures against sudden signal change to stop, additional beacons are installed as the signal. In other words, in this system, ATO function and safety-related function are performed by combination of ATS-DK and FS-ATO. This newly proposed concept is unique. This chart indicates the concept of newly developed ATS-based ATO. This blue row is a ATO function which isn't safety related, and this pink row is safety related function. In conventional ATO system, equipment which performs ATO function isn't required to be safety related, and ATC equipment is required to be safety related. On the other hand, in the new type of ATO, required safety is ensured by whole system with combination of FSATO and ATSDK. This concept is different from the conventional ATO and indicates one direction for realizing ATO without redesigning of existing ATS. This picture indicates prototype system installed in JR Kyushu's vehicle. Performances of the system has been confirmed step-by-step test. Main purpose of this test is to confirm control function of safety operation and to confirm performance of distance calculation, position detection, and accuracy of stop positions at stations. No problem in practical use because the function of this system were operating according to specifications through functional verification tests. This picture is an example of running test results. This white line indicates that FSATO, this is FSATO calculates running speed profile, and this white line actually train speed. So from this picture, we can see the train speed is controlled appropriately. So from until now, 2,500 kilometer running and 1,000 times train, 1,000 times station stop were performed. Through these tests, tuning and verification of stop position accuracy, driving time, and ride quality were carried out. Since the end of 2020, demonstration operation has been performed. In the demonstration, a licensed driver has been onboarding a commercial train on a Kashi line of JR Kyushu for proving runs towards the realization of GOA 2.5. I heard that JR Kyushu is aiming to start driverless operation in 2024. So I'd like to conclude my presentation. I introduced current state of ATO in Japan. Japan has a long record of operating GOA4 system. However, ATO isn't applied to general conventional lines. But operators' interest in application of driverless operation to general conventional line is growing. As Japanese unique proposal, GOA 2.5 system is now being developed. Especially for rural line, intermittent type ATP-based ATO, which is being developed by JR Kyushu, is expected to contribute to reducing costs and expansion of possibility of railway future. So thank you for your attention.
Thank you very much.
Thank you.
Gregory, for your presentation. As a result, we have finished all the presentations. First, I want to say that all of them were very informative for me because I'm an industry engineer. I'm dealing with more strategical or macro level problems, but here today I learned many things, some technical details, but it was very useful for me. And now, any questions do you have, dear participants, for all presenters? We have listened 5 presentations. The first presenter is not here now, but for the remaining ones, we can get the questions. Yes, a few questions are coming on the chat box. Let me read them. Interesting presentation. The intention with grade of automation 2.5 is to reduce cost compared to level 1. Which costs will be reduced when you still need staff in train? Do you expect a capacity gain? Actually, I was planning to ask this kind of question. Maybe I can make a addition to that. Also, for Istanbul metropolitan case, we talked about some productivity increase, or, for example, increase in the number of passengers, or decreasing some headway times. How can we make this? I understood that some operations can be more effective. We can decrease some operation costs, but how the number of the passenger will increase when you increase the automation level? Maybe you can answer both of them.
Thank you for your question. So I heard from operator now, so they required cost for to make training for driver. It requires costs. So in GOA 2.5 system, staff staff take a seat in the cab, but he doesn't have a driver's license. So training cost. So the railway operators expect that training cost will be reduced. I'm afraid, but how much cost will be reduced? I can't now answer how much cost will be reduced in concretely.
Okay.
Okay.
Thank you. And maybe Mr. Mehmet Demir wants to add something. I remember your slide. You show that peak hour capacity will increase 2 times after the conversion, and also headway time will decrease 2 times from 180 seconds to 90 seconds. I would ask that also. How will you be successful about that parameters?
Thanks for question. The main issue is that right now we use the fixed block system. It isn't CBTC system. When we convert from the fixed block to moving block, which is CBTC, so the headway increase from 3 minutes to 2 minutes. So our train capacity will, of course, increase. That's why the passengers number is increased.
Okay, then thank you. Another question or comment? Yes, question. It seems the solution presented in much based on ground equipment. Is there an evaluation plan to replace these with radio interfaces to limit investment? I think the question is going to Mr. Hiraguri again.
Sorry.
Can you
so,
chat box? Also, you can see the question.
Yes.
Or I can repeat it again. It seems the solution presented in much. You see?
It seems. Sorry. It seems solution presented in much based on.
Radio interfaces.
So
decrease the investment budget, I think.
So in the future, there is a possibility to using radio communication system. So, but at present, so to introduce radio communication system, railway operators is required railway operators will if they install a radio communication system, railway operator will be required not small costs. The first requirement is to use existing ground equipment. That is a present situation, but as I mentioned, in the future, there is a possibility they will introduce a radio communication system and reduce, for example, ground beacons or wayside signal and so on. Okay.
Thank you very much. Also, I will add a question. What is the budget? Actually, I'm asking for the Istanbul case because I'm living in Istanbul, and I wonder that if we transform all the railway system or metro system from automation grade of automation 1 to 4, what will be the total budget? Is it applicable? Is it feasible? Do you have an idea, Mr. Mehmet Demir? Or we can choose a pilot area line. We can start with them. Also, you told that there is an example between Üsküdar and Çekmeköy. What was the number? I don't remember, but it is driverless. So would you like to say anything about that? Mr. Mehmet Demir is not here maybe now. Or convenient. Okay.
If you're asking, sorry, if you're asking about the budget of the current projects, maybe I can answer, but there is no straightforward answer for all this stuff because, you know, the metro lines are not the same actually. So, for example, in our metro line, which is, as I tried to explain in my presentation, is not a very conventional one, not only in terms of the speed, but also in terms of the intervals between the stations, for example. For example, there is, I think, 10.5 kilometer distance between two stations in our metro, which are very close to the airport. So the total distance is 10.5 kilometers, whereas the whole line for the Gebze-Darıca metro, for example, is 15 kilometers. So there are 11 stations for that one, but only 10 kilometers between only these two train stations. So it's changing from one line to another line, the design speed. By the way, Aselsan was also involving in M1 transformation project because we were also in the consortium of Metro Istanbul, under Metro Istanbul. So we were all together making the transformation process. So they will give you probably the figures for that one, but for all the others, for example, for a line of Istanbul, the rough estimate is about only for the Gayrettepe to Istanbul airport line is about 20 million euros. And for the other one as well, it's again about 20 million euros or so. But as I told you, the characteristics of the lines are not the same. For example, Gebze-Darıca metro line is budget-wise, I mean, is a lot different than the other one. And also, when you are making contracts with the contractors in Turkey, for example, we are supplying the signalization system under contractor. I mean, we are giving our products to the contractors, not only to the direct operator. So sometimes they ask you to perform also the installation process, and some others tell you just to supply the equipment and perform the test, but they will also performing the installation processes. So this also is giving a lot of difference in budgets. For example, in our Gayrettepe metro line, we are only supplying the equipment, performing the tests, but all the installation, cabling, for example, which is a huge cost item, is not included in our budget, for example. So they are always changing from one metro line to the other, but maybe Metro Istanbul can give you better figures for their specific M1 metro line.
Okay, thank you.
Thanks, Mr. Özgür. For my question, as I said, it's also include the platform screen doors too. Our budget is about $60 million, 60 million euros. I'm correcting.
60 million. Okay.
Yes.
Then we have to make a choice actually in terms of the investment. Still, we need some extra metro lines maybe. Instead of increasing the automation level in the current ones, we can increase the number of or kilometers of the new lines, or we can increase the automation level for the current ones. This is also a critical decision, I think. Right? Okay. Okay. Any other question? Also, you can raise your hand, or you can talk also, or you can choose to write to the box. Maybe I can ask another question for Mr. Tarakçı. You talked about the CBTC, and also I'm working in logistic issues, and I wonder that if these systems are applicable for the freight transportation in the rail system, or these systems are only convenient for the passenger trains. Can you make any comment about that?
Yes, right now
our system is very important also in freight transportation, and we can see many accidents. Maybe it can be usable for this area. Yes.
Yes, good question. We have actually at the moment our 3 projects, and all these projects are metro signalization projects. What you're asking or stating is the one for the main line. Right now, as I said, we do not have any projects regarding the main line signalization. So we are very eager to also perform another signalization project for the main lines. Maybe 50 or 70% of our product can be reused in the other one. We cannot use it 100%. It's not 100% reusable for the main lines, but especially the ATC system, which is in our project supplied by TÜBİTAK, is also designed for the mainline projects. TÜBİTAK is using the very first prototype, or not the prototype, but the first of its kind in the mainline metro line. So we also accommodated it to the metro line. So the ATC, we have a solution via TÜBİTAK for the mainline projects, and we have to, of course, make some modifications to our onboard equipment in order for them to be used in the main lines. So I think the reusability ratio would be about 50 to 70%, but they cannot use as is in the main line signalization projects at the moment.
Okay, thank you very much for your answer. Okay. And if Professor Schmidt is here, maybe we can ask a question to him. Professor?
I'm here, yes. I'm here.
Okay, I couldn't see on the screen. Okay, also your presentation was very interesting for me. You make a comparison with the road vehicles and railway system. I think that the application of the connected and autonomous vehicle application to the rail system is easier. This is my opinion. First, I will ask that, are you agree with me? Because there are many other external things in the road transportation, but generally the railways are closed loops, closed circuits. So maybe applying this system to the railways can be easier. Do you agree with that?
Actually, I fully agree with that. I wanted to highlight this a little bit in the presentation. I didn't want to point it out too much, but I also think so. I mean, for example, if you talk about object detection, the number of scenarios that you can encounter in a railway system are very much limited compared to, for example, an urban scenario where you're coming across pedestrians that are crossing the road. At the same time, you have cyclists, then some other vehicles come from left, right, trucks, and so on. So there are many more scenarios that have to be considered. And there, if you talk about the deployment and test of the equipment and the algorithms, also the number of scenarios that have to be tested is much higher in autonomous vehicles, road vehicles. Okay, so identifying corner cases, for example, is a very big problem. I mean, finding all the corner cases that can happen in order to ensure safe operation of the system is very difficult for autonomous vehicles. And for train systems, the number of possible scenarios is, as I said, limited in comparison. So I would agree with your statement.
Okay, I think the number of the works about that in a railway system will increase by the time, but maybe in terms of the Pareto rule, the benefits from the road transportation, road vehicles may be higher because it is more complicated system. If you can apply the autonomous system to the road transportation, maybe the benefits will be better. Because of that, everybody is focusing on the road vehicle autonomy. Maybe.
One is that, the other one is the price. I mean, you heard about the investment prices for trains. Okay, so working on an autonomous vehicle is much more, much cheaper, I would say. I mean, buying a vehicle is not in the order of tens of millions of euros, but it's in the order of some 100,000 euros. Okay,
Yes,
so even a university laboratory can afford that.
Okay, yes, you're right. Thank you. As we discussed the questions for ATO for capacity increase, ATO is one of the one way to achieve its plus reliability, safety, energy savings, but there are other small steps that can help as well. And there's a link here. It is shared, so maybe you can read it also. Okay, any other question? Would you like to ask? Okay. We are just in time also. If everybody is okay, also I'm okay. I asked my questions. And again, I want to say thank you for all your participants and for the presenters. All of them were delicious for me and very informative. Because of that, I can say thank you again, and I'm very pleased to be here today. Because of that, I want to say thank you to Mr. Atila KESKİN because he has invited me to here. And also, I want to give the word to him for the closing speech. Thank you for everybody.
Thank you very much.
Thank you, Mr.
Thank you very much.
A big thank you to everyone who helped us to make this seminar. And I would like to thank to our distinguished speaker for their excellent presentation and for making this seminar exciting and meaningful. Thank you all.
Okay. See you in another webinar. Then.
Yes.
Okay.
Okay. Thank you.
Have a safe and healthy days.
Thank you.
Thank
See you. Bye-bye.
Thank you for your wishes, Mr. Özgür.
Thank you very much, sir.
Thank you.
Bye.
Bye.